Hi, this is Sarthak Jain, and this is a demo of LAB3 for EE533 under Professor Young Cho. In this lab, we were supposed to design a mini network intrusion detection system where we were supposed to replicate a network test bed with a lot of input data stream, and that input data stream will have an intrusive malicious pattern that we need to detect. And the moment we detect the malicious pattern, we need to drop that particular packet and let the rest of them go through the entire system. For this particular case, we were supposed to design a 7-byte pattern matcher because we are supposed to be detecting a 7-byte malicious pattern from our input test bench. The structure of the entire code that we have made is exactly like you see on the screen, where we have an input FIFO, a 7-byte pattern matcher, and a drop FIFO. The test bench basically simulates the network test bed where we throw a lot of the packets from the test bench into the input FIFO, which then buffers the packet and then sends it outwards towards the 7-byte pattern matcher for detecting the malicious packet. Following this pattern being matched or not matched, we go into the drop FIFO where we decide whether to drop that particular packet or let it go towards the memory. Before we begin, I'm going to explain first the schematics and the code for this 7-byte pattern matcher, followed by this drop FIFO, and then we'll go into the waveform to see how it works. Essentially, this is the 7-byte pattern matcher, where hardware reg A at the top you see is the will contain the actual pattern to be matched, which is malicious in nature. This is the reference to which will match the inputs. We have a 72-bit input, which is basically a 9-byte input buffered through this 9-byte register, and we also have a bus merge module whose job is essentially to concatenate the input packets to create a 14-byte input. I'll explain why 14-byte in a second. The output of this concatenated 14-byte data goes to this module called word match. This word match module is basically the heavy hitter where the logic for the pattern matching actually resides. So first, let's begin with some corner cases, some observations. Uh, since we need to find out a 7-byte pattern, there is a very big possibility that in order to avoid detection, somebody breaks down that malicious packet into this particular way on the screen. 1 byte of the malicious packet is in packet 1, and the rest of the 6 bytes of the malicious pattern are in packet 2. This is one of the corner scenarios we need to cover, and that is why we need two particular frames or two particular 8-byte packets together to be checked. Another corner scenario is something like this on the screen where you see six bytes in the first packet and the 1 byte in the second packet. So essentially, the idea of this network intrusion detection system is to detect a 7-byte malicious intrusive pattern in the incoming network data stream. The input stream is a 8-byte packet plus a 1 byte pattern for a control signal, which is to tell the FIFO some information about the packet. This totals 9 bytes as we saw in the system. This is a 9-byte packet where the 8 bytes are the actual data and 1 byte is the control signals. Now, this data goes into a fall through FIFO and then which then goes into the pattern matcher 7B module as you see on the screen. We need to consider the possibility that the malicious pattern is hidden, right? And that is probably this is exactly why we need this 14 bytes of data, as I explained before. One chunk has a few bytes of matching pattern, and the next incoming chunk might have the rest of the pattern to be matched. So therefore, this bus merge requires that we concatenate 6 bytes of the previous data, which is 1 cycle delayed data, and the newer data. So this essentially covers this corner scenario where the packet might be broken down, the malicious packet is broken down. And following which this concatenated data goes into the word match. If you see on the word match, we see that the hardware register A, which is the pattern to be matched, has again been broken down into two. Sorry. One is a 7-byte pattern and one is a 1-byte chunk, that is a separate control signal. Now, the reason we do this is because in the code we are giving this particular pattern to hardware register A. And you see these 7 bytes, the lower 7 bytes are essentially the pattern to be matched, and the upper 7 bytes are the mask, also called A mask here. So now we need to understand what the A mask actually does. The A mask of 7 bits is used to decide which byte of the pattern will be compared with the input data stream. So essentially this particular one at the MSB will match this upper 7 bytes, these upper 8 bytes with the upper 1 byte of the incoming data. The second one will essentially say that, okay, the second to the MSB byte is going to be matched with the second to the incoming byte of the input data. So each bit corresponds to checking that particular byte from the pattern in the input data. The reason we do this is because we need to make our pattern matching to be a little smarter instead of naive and having everything being matched. This will become a little more clear when I explain the schematic again. So to understand what I just said, we need to go down into the word match schematic. The word match schematic basically takes the 14-byte input data, the input stream data. This is the pattern to be matched, the malicious pattern to be matched, and this wildcard is basically the A mask, as I was explaining earlier. Each single byte, as you see, corresponds to that particular byte, which will be matched with the input data stream. So the 7 bytes are compared with the 7 bytes pattern. And if this wildcard is 1, we actually match this pattern. If the wildcard is 0, we do not care whether the pattern is to be matched or not. Another reason to have this pattern matching is because there is a possibility that the input data actually resembles the packet, the malicious pattern. And so we do not need to drop that particular packet. That is why we will make some of the patterns, some of the bits in the wildcard to be 0, the A mask to be 0 when the incoming data is equal to, actually resembles the malicious pattern. Now next we need to go down into the comparator. So the word, essentially this word match module is exactly this module here, and this comparator module is essentially this particular module on the screen. As you see, if the mask is 1, this guy becomes 0, and essentially for a match to be 1, we need these two comparisons to be true. If in case the mask is 0 for this particular byte is 0, this guy becomes 1, and then we don't care whether the match is actually 0 or 1 because this output will be 1 anyway. So this essentially turns the naive module into the naive pattern matching into a smart pattern matching. Following the matching pattern algorithm, whether the packet was matched or not, we go into the drop FIFO. Now the drop FIFO is where the actual packet dropping mechanism is, and whether we need to whether we send the incoming data into the FIFO for further processing or not. Essentially, in this drop FIFO, we have this dual port memory, and this dual port memory has 2 pointers. This particular module is a write pointer, which increments as the data goes into the FIFO. And this particular module on the screen, FD8CE, is the history pointer. Now, essentially, if we locate this this chip enabled signal here, we'll see that this chip gets enabled if the word is a first word or a last word and the packet is not to be dropped. Otherwise, this chip enable becomes 0 if we are in the middle of the packet or the packet needs to be dropped. What this essentially means is that this particular module will basically return my write pointer to the original location if the packet needs to be dropped. So for example, if this is the packet stream and my write pointer is somewhere here and these two packets need to be dropped, the history pointer will essentially update this module and take my write pointer from here back to the place where the packets were not to be dropped or there was no detection of the malicious pattern. So this history pointer is essentially extremely important for the data to go into the FIFO. Following this, we will go into the waveform to see how this actual circuit and the Verilog code works in a waveform. On the screen, you will see the simulation waveforms for the particular circuit that I just showed, which is essentially the input FIFO, the 7-byte pattern matcher, and the drop FIFO. All these signals are of interest, so let's go into some of the signals that we require. The first one will basically tell whether the packet entering the pattern matcher is actually the first word of the packet or not. The D input is essentially the input from the test bench into the FIFO, into the start FIFO. In underscore FIFO is the actual signal of interest where the pattern matching actually starts. And one observation here we need to make is that there is a gap and there is a delay of 3 packets before my input FIFO packet starts actually matching. So if you see, if I take the cursor here, you'll see that this particular data will get updated here after 3 clocks. So this 104, this data which is 10004, essentially 1, 2, and 3. So there is a 3 packet delay before the pattern matching actually starts to match our input data. Finally, we have the last word. This signal will be up when the packet has been completed and the last word has been the FIFO sees the last word here. Now XN27 is the history pointers wire. Basically, this particular wire on the screen that is marked is the XN27, which essentially is the history pointer. The WADDR is the write pointer of the dual port memory. This will increment the moment a FIFO is written into, and followed by the control signals, the beginning of the packets. The matches signal here essentially determines how many malicious patterns have been matched with the input data. So out of 100 packets, it only finds the malicious packet once, it will say 1. If it finds it twice, it says 2. A counter for malicious patterns being matched to the input. In the waveform, we see that only one packet has been found from a number of packets that were sent from the test bench. So that's why the count here is 1. This pattern match signal is going to remain 1 for these 3 cycles, as we said before, because it is how many cycles it will take for the new packet to come in. So it needs to stay high for that particular duration when it finds the malicious packet. The drop packet signal basically will tell the packet to the circuit to drop that particular malicious packet and update the pointer. Now, to show how it works, we'll see that in this particular waveform, we see that this input FIFO, I think we'll go from the packets that were actually matched. So this pattern match becomes one here. Uh, let me show you how it starts matching. So if you look at the 12.5 microsecond mark, we'll see that our input FIFO data actually matches the hardware edge A, which is the packet, which is the pattern to be matched. We see that the upper 7 bytes of this pattern to be matched actually matches my data in the FIFO, which means at that particular moment my matcher underscore becomes 1, matcher underscore match becomes 1, and in the next cycle my counter will start becoming 1. Now, following the match, once the circuit detects that this is the malicious packet, we need to drop this entire packet from the first word to the last word. So essentially, this circuit waits till the last word signal becomes 1, and the moment this last word becomes 1, we see that the end of packet becomes 1, and I think in the same cycle we see the drop packet signal also become 1. One interesting observation here is, as we said, that the history register pointer, the moment it sees that the packet needs to be dropped here, will essentially update the write pointer of the dual port memory uh, from its history. So this is where it started remembering that this is the new packet here. It said I'm 41 at this particular point, and the write pointer kept increasing 42, 43, 44 because the number of packets being entering into the system continuously increases. The moment there is a drop packet signal becoming 1, our write pointer basically updates. This history write pointer basically takes our memory write pointer to the location where the packet was not to be dropped, which was 41. So essentially, this indicates that 10 of my packets were dropped from 42 to 52. All these 10 packets will be dropped because my write pointer has essentially moved from 52 to 41 again. And this is how my 7-byte pattern matching along with the drop FIFO would work. Finally, one last observation here is that my FIFO's control signal remains 0 for this particular pattern, which is essentially 10, and then it actually changes for some of the other patterns. So essentially what that is because of the test bench for the FIFO that we have written, where if the count is less than 9, if the count is less than 11, we actually make the write enable signal 1. Then if the count is less than 14 or exactly equal to 13, we enable the read enable signal, and so on and so forth. And these counts are basically what are reflected in the waveform where the write enable is zeros and ones. So because the count actually matched 10 of the test bench, these 10 packets will be dropped. If somehow our pattern was matched somewhere here, then more packets would have been dropped. Essentially, the packets would only be dropped between the first and the last packet. All of them would be dropped, and the history pointer would then update my dual port memories pointer. So this is how my pattern matching works. Thank you for watching, and subscribe to my channel.